Hello everyone. So this is third recording about the first topic, introduction to materials. So we stopped the last time at the materials selection process, how you can select a material based, of course, on a few criteria. So selection is not done randomly, but it is done based on very clear criteria related to, of course, to the project and to the materials used and to the environment, of course, as we said the last time, in addition, of course, to the economic factor, the cost of the material to be used. So the first thing to determine the selection of the material or to govern the selection of the material is the application. What we mean by the application here, if you have to clearly determine for what application your material will be used. And the application, based on the application, the properties of the material will be required, will be determined. Because for X application, you need maybe this and these properties. For Y application, or for Z application, you need other properties like mechanical, electrical, thermal, magnetic, optical, resistance to aggressive environment and deterioration due to the environmental agent. So application is very strongly related to the properties of the material. First, we have to decide or determine for which application this material will be used. And then the properties will be determined based on the application, of course. So once the application is determined, the properties will be, of course, also required for that specific application will be determined. And based on the properties, you can identify the materials that can be used, material or materials that can be used in that application. And of course, the material will be having a specific structure, specific chemical composition, because these two parameters, structure of materials, the composition, chemical composition or the mineralogical composition of the materials are different from one material to another one, you know. And then, of course, these candidate material will be determine also the processing. What kind of processing or what type of processing is needed or required for this specific type of material to be manufactured. Because the production process or the manufacturing process of materials is different, of course, from one material to another material. The process of manufacturing is different. How you produce steel is different. How you produce concrete is different. How you produce cement is different. How you produce aggregate, even within the metals themselves, the process of fabrication is also different from one metal to another metal. Same thing for the ceramic materials. How you process or how you produce polymers is also completely different than how you process metals or ceramics or any types of specific types of ceramics like concrete. So the process, because the process is affected by the change in the structure and the overall shape. Example, casting, centering, vapor, deposition, doping, forming, joining, strengthening. This is mostly a process that you can find mostly in, of course, in metals forming and metals processing. So So the bottom line from this slide here, what you can understand, what you can get out, what you can walk away with, is the three parameters here. Application, properties, materials are interconnected. To select a material, first you need to know where this material will be used, what kind of application this material is going to be used for. And then based on the application, of course, the properties of the material could be determined. And once the properties of the materials are known, let's say for your material, you need mechanical and thermal properties. So you don't need optical properties or electrical properties. Then based on this, you can identify what are the materials. They have these properties, mechanical and thermal properties. This is just a very overall general example. And then once you determine these materials, X, Y, and Z materials are candidate. They are not selected yet. They are just candidate that can be used for this specific application because they have the required properties. Then it comes to select which process of fabrication should be used for these materials, or one of them, to be selected for this application. So what I'm going to ask you, just as an optional assignment here, so just use these three different criteria that are interconnected, and select an application, any application. I'm not going to give you examples, just think about an application, about usage of material, and then apply these three different criteria. Of course, you have to give some details, and you have to be very specific. Here we are just talking about general. So be specific, select a specific application, then determine what are the properties that are needed. It could be other properties here. This is not an exhaustive list, of course. So determine what are the properties are required for this specific application, and then identify the candidate materials. What are the materials that susceptible to be used for this application? And then talk about the process of manufacturing one of these materials that could be used and could have these properties required for this application you selected. So you can see that these criteria are interrelated. So the processing is affecting the structure, changing the structure of the material, and the change in the structure of the material will, of course, change the properties of the material, and the properties of the materials will, of course, affect the overall performance of the material when it is used in such an application for a specific purpose. So all these three or four criteria, of course, performance is at the end of how this material will perform overall in the usage that has been used for. So it's like you have a triangle here or a pyramid. So properties or process affect the structure affect the properties, and also the properties affecting the process, or the process also affect the properties, and so on. So this is what material science is involved, as we said the last time, is involved mainly in this left-hand side, properties, structure, relationship between properties and the structure of the materials and how they are affecting each other. And the materials engineering is mostly connected or interested on the right side, how the process affect the properties of the material. So mostly materials engineering is looking to this part here, properties and processing, how you process, how you design a material that has tailored or specific properties, and vice versa, how the properties are affected by the process. If you change in the process, how this could affect your the properties of your material. So all these are interrelated and interconnected. Composition, of course, is related to the composition of the material, is related to the bonding, chemical bonding of the atoms within the material, and also to the crystal structure, whether it is amorphous or crystalline. We'll discuss, of course, some of these later on in other topics that are coming, of course. And these affect the chemical and the thermal processing of the material, how you process this material, how you manufacture it. And the thermomechanical processing will, of course, induce changes in the macro and microstructure of the material. And any change in the macro and microstructure of the material will definitely affect the mechanical properties, electrical properties, magnetic properties, optical properties, thermal properties, and any other properties that you may think about related to the material's properties. And these, of course, all of these all together make a change in the performance of the material or affect the overall performance of the material. Just to give you an example here about the optical properties, because maybe the mechanical properties you are a bit more familiar, but we're going to give you an example about the optical properties. So look at this text here and these three different specimens. These specimens are made up with aluminum oxide. Aluminum oxide is Al2O3. Aluminum oxide, or sometimes we just shortly we call it alumina. So if you look to these three different specimen in terms of optical properties, what we mean here by optical properties, the light transmittance, how they transmit the light through these samples here. So the three samples are made up with the same material, the same chemical composition. What is different here? If you look at these three different specimens, what is different between the three? The difference here, as you can see, is the light transmittance. So definitely you can see that this sample here, let's say sample 1, has the highest or the best light transmittance. Then it comes sample 2. So sample 2 is not too bad, but it's really blowing just very, very few. We can have a low level of light transmittance. But if when you look to the sample 3, so nothing. Myself, I cannot see anything. So light transmittance is almost 0. Or let's say just it's the lowest compared to the two others. So the first one is the best, second one is less, and the third one is the worst or the least or nothing. So what's different here between the three specimens which are made with the same material, alumina? So the material is the same. What is different here is the difference is in the structure of the material. So the structure of the materials, which makes a difference here in terms of transparency or in terms of the optical This is what we call it the optical properties, how they can transmit light through the material, of course. So the difference here between the three is the crystalline structure, or the structure itself. How porous or how dense is the material, or how crystalline and polycrystalline the material. So this is what makes it opaque or transparent. So you can see that the structure here is changing the properties of the material. And this is connected what we were saying just earlier. Structure affect the properties of the material. And the properties of the materials, of course, will affect the performance. Here the performance is the light transmittance. So overall, we can say that the three parameters here, design, materials, processing, are interrelated and interconnected. So each one affects the others. If you change the processing, the design of the material will change. If the design of the material changes, the processing of the material, what kind of equipment you have to use, the cost will also be affected. You change the processing of the material, how you process the material, also the properties of the material will be affected. And vice versa also. Changing the properties of the materials, the processing has to be changed also. And also the difference or the interrelation between materials properties and design. So design is interrelated to the materials properties, because design is related to service conditions, as we said. What kind of role, what kind of job, function this material will be doing during its service life. And this, of course, will affect the materials properties, the choice of the materials properties. So these three are interrelated and strongly related between the materials design and processing of the material. So now we go to the other side of the materials, the types of materials. We were talking about types of materials many times, but now we will discuss these types of materials. So you can see here just a very familiar example to you. I'm not advising you to, of course, to abuse with the beverage. So please consume with moderation, because it's not a healthy drink. Anyway, so you can see the same product could be packaged in three different types of materials. The beverage here, it is packaged in three different types of materials. First here is packaged in what? This is can, which is made with metal. And this is also, the beverage is packaged in what? In glass, which is a ceramic material. And here it is packaged in what? In plastic material. So same material, same drink, same liquid could be packaged in three different materials. And this is the importance of materials. You can see the importance and the versatility of the materials. Could be used for different purposes. Material is not designed to, or it's not specific to one single use. It could be used for different use, but with changing the properties and the processing, of course, of manufacturing. Same thing here. You can see oil could be packaged in plastic, in glass, or in metal, of course. And same thing for the other beverage. So different purpose, different use, but of course, different processing and different properties. So overall, we have 5 materials that we can say that changed our world. If you don't agree with this, so let me know, comment. But we all believe that, I think, that these five materials have changed our world, have changed our life, have made significant change in the way we are dealing with materials and with devices, with equipment. So these five categories that are available for engineers and also for general public, but of course we are focusing more on engineers, what materials they are using and how they are using the materials, how they are processing the materials, how they select the materials from the significant portions of materials available. So the first category of materials is called metals. So here we are talking about all metals. We are not specifying iron or aluminium or copper or whatever. So we are talking about all metals. So aluminiums, of course, or metals, sorry, they have very specific properties. We'll discuss them later on in a bit more details, but for instance, what characterize metals, they are crystalline, they are not amorphous, they are not non-crystalline materials. All metals are crystalline. And also, the chemical bonding in metals is metallic bonding. So you cannot find, we'll study, of course, metallic chemical bonding in a separate topic. But for instance, we're just talking about the major properties of metals, that they are bonded with metallic bonding. They cannot be bonded with ionic bonding or covalent bonding, but they are bonded with metallic bond. Second category of materials, ceramics. So ceramics are, well, not all crystalline. You may find some ceramics, they are amorphous, but mostly, of course, they are primarily in crystalline form, and then they could be transformed into an amorphous structure. So most of ceramics also are bonded with ionic bonding. There are some exceptions, but of course the general case is ceramics materials are bonded with ionic bonding. So you can see here at least the change, the difference between metals and ceramics in terms of the chemical bonding. And if you have a different bonding, of course the properties will be different. Some they have covalent bonding, of course. Some ceramics they have covalent bonding, but the general case, of course, is ionic bonding. The glasses is not a category by themselves because they are under the category of ceramics, but sometimes in some references they made them a separate category. Why? Because they have a specific structure. All glasses are non-crystalline material, are amorphous materials. The third category of materials is polymers. So polymers are, you can see, is different than metals and ceramics. They are non-crystalline materials. So they have an amorphous structure. And mostly they are bonded with covalent bonding. The fourth category of materials, it is called composites or composite materials. So composite materials, we cannot attribute specific structure or specific chemical bonding to composite materials. Why? Because they are composite. What we mean by composite here is a combination between two or three, but at least two. You cannot make a composite materials with only one. So it has to be combination between metal, let's say metal plus ceramic, or metal plus polymer, or ceramic plus polymer. So it's a combination between at least two of these categories. So this is the most general case, of course. It's combination between two. It's rarely where you can find a composite that is composed of three different categories of materials. So we cannot attribute specific chemical bonding. So the chemical bonding here will be, of course, the chemical bonding of the two categories. And also the structure will be a combination between the two. The properties also will be combination between the properties of both both categories that are combined together. Then we have the fifth category of materials, the last one if you want. So this is of course specific to electronic materials. So it is semiconductors. So it has specific use. It's not structural material. So these four, 1, 2, and 3, and 4, they are called structural materials. But semiconductors are not used for structural purpose, are not used to build any structure, are not used to build a car or buildings or bridges or any kind of structures. So they are used for electronic devices and purposes. So this is why they have electrical properties. They don't have mechanical. We don't look at the mechanical properties or the optical properties of semiconductors. We look to the electrical properties. So this is the 5 major categories of materials that are used for different purposes. So just very brief, some properties of these different categories. If we take metals, so usually they are strong, they have a high strength, most of metals of course. They are also ductile, most of metals of course, not all metals are ductile. There are some metals, they are brittle, but most of metals are ductile materials. And we'll discuss later on what is ductility and what is a ductile material, what is a brittle material. But if you have already done mechanics of materials, of course, I think you understand this concept properly. They are also tough. What we mean by tough is toughness. Toughness is different than stiffness, of course. So this concept also will be discussed in the mechanical properties later. They also usually have high density. High density compared, of course, to the polymers, compared to the ceramics. So the density of metals usually it's high. Of course, we have some metals, they have lower density, like aluminum. It has a lower density, 2.7 or something like that. But most metals like steel or iron, it has of course a high density, 7.8 and more or a bit less. Also, they are known by conductors, conductivity, high conductivity. So they can conduct electricity and they can conduct also heat. So metals are good conductors. So you can see these are some properties and specificity of the metals. You may find some of these properties also available in polymers and ceramics or composites, but not all of them, of course. So when we come to ceramics, so usually they are not that strong as metals, but still they are hard also. So the hardness is quite high. But most ceramics, if not all ceramics, are brittle. So you can see here a difference between metals and ceramics. So ceramics are not ductile materials. So they are brittle, they break suddenly without plastic deformation, without ductility. And in terms of density, they have somehow low density. I cannot say low density, but if I want to compare it, the density of ceramic with metals, of course, we can say it is a low density. But if you compare the density of ceramics with polymers, of course, the density of ceramics is higher than the density of polymers. So we have to be specific here. So it is lower than the density of metals, but it is higher than the density of polymers. Ceramics also are opposite to metals. They are insulators. They are not conductors. They don't conduct electricity or heat. When we say insulator, that doesn't mean 100% insulators, but in all cases, they are not conductors. So they have low conductivity of heat, but they are completely non-conductors of electricity, of course. For polymers, so polymers are not strong, are not hard, and so they are very weak. They are soft, flexible. They are also ductile, so they share with metals the ductility properties. While they are not strong as metals, but they have the ductility, the ability to generate a large deformation. Also, density is low, so here we can say low density because the density of polymers is lower than the density of ceramics and also lower than the density of metals. And polymers are insulators. So you can see here they're quite sharing with ceramics these properties. So polymers, they don't transmit electricity or heat. Now we come to the composite materials, which we said it is composed of two different categories. So composite materials generally, of course, they have some strength. We can say they are strong because you cannot combine, if you combine ceramic with polymers, so of course the composite material also will be quite strong because it gets strength from ceramic, while the polymer of course is weak. And you combine of course metals with polymers also, the composite will get the strength from the metals because it's a combination of two different materials. Usually they are ductile also because usually we combine ceramic with polymers or metals with polymers or metals with ceramics. So we combine also always two different materials that can, when combined together, they provide the best and the better properties and compensate the weakness of one of them. Density, we cannot really say low density. It's better to say moderate density because you are combining two different materials. Unless you combine ceramic with polymers, so the density will still be low because it is still lower than metals. But if you combine metal with polymer, so metal has a high density and polymer has a low density. So it comes to somehow it's a moderate density. And for composite, we cannot say they are conductor or insulator because it depends on the combination. Because if you have a metal in a polymer, so metal is conductor, but polymer is not a conductor. So in it, there is one component that could conduct electricity and heat. So it's not completely insulators, it's not completely conductors, it depends on the combination made. But if you combine ceramic with polymer, so of course, definitely, you will not have any conductivity because both materials are insulators or non-conductor materials. Then lastly, the semiconductors. Semiconductors, of course, as we said, it is they have electrical properties, but in terms of strength, they are weak. They don't have any significant strength. Also, they are brittle material. They have low density. And in terms of conductivity, of course, they are called semiconductors. They are not fully conductors. They are just semiconductors. In between, they are not insulator. They are not fully conductors. They are just semiconductors. And on my right side, you can just see some examples, selected examples of these 5 categories. Metals, you can see here different examples of metals: copper, lead, tin, zinc, steel, nickel, and some examples of pottery for ceramics materials, some examples of polymers, which plastic materials, different plastic materials, rubbers, example of composite materials, and example of semiconductors. So just to connect it with the last or the before the last category of materials, ceramic or composite materials, and how it is formed. So you can see here the 4 major categories: structural materials, of course. Here we don't have semiconductors because it's not structural materials. As a civil or architectural engineer, of course, your business is not with the semiconductors. Your business is with the structural materials, metals, ceramics, composites, and polymers. So how to form a composite materials? Of course, we said it is like the midsection here. So either you combine ceramic with metal. So here you form a composite materials, or you form a composite material with here in this area here ceramic with polymers, or metals with polymers, or sometimes you may combine the 3 all together, metal, ceramic, and polymer, and you form your composite. So definitely you know that the composite will be in most cases how it is manufactured. So you have matrix. So the matrix could be ceramic, could be polymer, or it could be even metals. But in most cases, the matrix is ceramic or metal or polymer. And the reinforcement or the fiber or the other material will be somehow metals. So you form a composite material that has the properties of both. So this is the advantage, and this is the idea behind forming or making composite material and developing this category of materials. This category of materials is quite a new technology in materials. It was not used a long time ago. It's just innovation in the 20th century. Because the polymers, if you remember, I think mentioned earlier that the polymers were developed around 1960. So before that time, of course, we didn't have composite materials. We were just using either metals or ceramics. And later on, of course, composite materials have been developed, and nowadays, of course, are largely used in different applications. So this is the idea. So you have a matrix, and then you have reinforcing material that could be fibers or filament or other types of combination. So this is the most common, but there are other strategies or other techniques how you form a composite material. So what you get from this combination, of course, you will get high strength because you're combining weak material with the high strength material. Or maybe it could be if you're combining metal with ceramic, so both have high strength. So you'll get a high strength in all cases. But if you combine, let's say, polymer with metal, so polymer is weak and flexible, but metal is strong. So still you get strength, you get high strength. You get also high stiffness, and the density will be lower than if you use, if let's say this is the whole material is made up with metal. But in second case, if this material, the whole material is made up with a composite, so the density will be lower, of course, than if you use single material like metal. So density will be reduced. So this is for metals. And then for the matrix, usually it has different properties, of course. So you combine these two together, so you will get all these together in one. And this is the idea of composite material. So the reinforcement material, it has a set of properties. And the matrix, it has a set of properties. This is just an example, of course, because the matrix, it depends. What is your matrix? Matrix could be ceramic, or it could be a polymer. And then reinforcement, it could be a metal. So in that case, you are combining these properties with these properties, or these properties with this. So it depends on what you are combining with what to get what. And of course, the purpose of making composite is to enhance the properties and to get a better properties of the materials, to get a set of properties that could fit in or could fit with your application. So just before we finish this part, so here is just some examples of density of some metallic materials. So you can see the density of metallic materials. Usually it's high, most of metals. So the lowest is, as I said, aluminum, 2.7, but all other metals, most common metals, of course, most known and most used. So you can see they have high density. So you can see here, even you have some metals like lead, silver, gold, 19.32. And the lowest, you can see magnesium is having low density with aluminum. So only these two most commonly used, which have a low density, but all other metals, they have a high density, as we just said earlier. So density, of course, without reminding you, density is the mass over the volume. If you want to find out the mass is equal to the density times the volume, or if you want to find the volume, it is the mass over the density. So, of course, these properties are connected together. Strength is affected by the density. So usually if you have a high density, you can see here on the x-axis, you have the density in kg per meter cube. And on the y-axis, you have the strength in megapascal or Newton over millimeter square. But please usually use megapascal. It is the universal unit and the most common unit used for stress and strength. So you can see here, mostly the density is, the relationship between density and strength is mostly linear. What we mean by linear relationship is, or proportional relationship, when you increase the density, the strength also increases. So you can see here, materials with a low density like foam, they are weak. They are in zone here, the weak zone. So they have low strength. So this category of materials, wood and wood product. So more the density is increasing, more the strength is increasing. You can see here rubbers, plastic rubbers, so on. And more you go for the area of ceramic materials, so the density is a little bit increasing. So this is mostly here we are in a polymer area. So most these materials are polymers, of course. You can see rubbers and natural polymers, foam. Then you go to the area of ceramics. So it's quite a medium density, and you see that the strength is increasing in this area here compared to the area of the polymers. Then lastly, you go to the area of what we call it metals and alloys. So this area here, metals and alloys, so you can see the density is higher. So most metals, they have density higher than 2 and 3, except of course, as we have seen just early, aluminum and magnesium. And most of metals, they are quite high density, and you can see the strength is also proportionally increasing. Then you go to area where you have some composite materials. So composite, it will be a combination between the two. So the density and the strength will be depending on those two different combinations of materials. So density affects strength. General rule, high density will produce high strength. Also, strength, of course, it has a cost. Strength is not free. More you get a high strength, of course, more the cost of the material will be also higher. So increasing the properties, mechanical properties like strength, will increase the cost of your material. This is why balance always has to be kept. So you can see here on the x-axis, the cost. Here it's given in pound, the UK currency, pound per kg, and the strength here. So same thing. You can see here materials with low cost, they have low strength, of course. More you increase the cost, more strength is increasing. But this is not always, of course, the case. It depends on the category of materials. You can see here some polymers are expensive in this area here. These polymers, foam, rubbers, and wood, they have low strength, but they are costly materials. Somehow costly materials. Not all, of course, polymers are costly materials because the plastics are very cheap. But some specific polymers are costly materials because they have other properties, not only strength, because strength is not the only properties, but strength, of course, as you know, is the main property. And of course, you can see here some other materials with high strength and also high cost. But in other ways, also you can see some ceramics here. They are cheaper, but they have good strength. So there is no really proportional relationship, linear relationship, as we have seen between the cost and the strength, because sometimes the property needed is not strength. Other properties like ductility or conductivity or some other properties. Strength is important, but it's not in all applications. It depends on the application you are looking for. Also, we have a relationship between the modulus of elasticity, Young's modulus, and the density. So usually here also we have linear relationship. More the density is increasing, you can see here heavy material from light to heavy materials, more the modulus of elasticity or Young's modulus is also increasing. So here you are in the area of polymers, so the density is quite low, and also the modulus of elasticity is low, so you have flexible material. Flexible is opposite to stiff. Stiff is hard. And if the material is flexible, that means the modulus of elasticity is low. So, and you can see here, more you are going to the area of high density, more the modulus of elasticity is increasing, and you are in the area of stiff materials, hard and stiff materials, rather than flexible one. So here quite a relationship is proportional and linear relationship. So I will stop here, and next time we'll talk a little bit in more details about these 5 categories of materials. And also we add other categories, new categories, but we will focus more, of course, on metals, ceramics, polymers, composite material, and semiconductors materials.